Hi everyone, we're going to talk about enolates and start on that unit today. And you might have guessed it, carbonyls are still a key player, very important bond. Now, we have been attacking that poor carbonyl carbon for so long, we are moving on to expand the victims of that attack to the neighboring carbon. So the carbonyl is still there, but it's the neighbor that's going to be attacked, or at least deprotonated, and then that one is going to have the reactivity. So you'll still see the carbonyl, but so because it's still a carbonyl containing featured functional group, we're going to kind of recap where we've been and then so we set ourselves up to move on. So let's go. All right, so I hope you remember that many of the previous carbonyl electrophilic attacks of a carbonyl, nucleophilic attack of an electrophilic carbonyl, revolved around two major mechanisms: attack open close kick, attack open protonate. So what do we call those? Which one was which? So let's review that. Mechanism number one, I'm going to do, let's see, it's going to tell me the specs here. Z is a leaving group. Okay, that's kick. You kicked it off, right? So it must be AOCK. That means that we had a nucleophile replace the leaving group. That must be called, because a nucleophile replaced the leaving group, that must be called the type of substitution. So nucleophilic is the nucleophile. Acyl is the group that got attacked. Substitution is the category of reaction. Okay, what did that look like? That means that the nucleophile replaced the leaving group, because Z equals leaving group, right? Equals leaving group. Nucleophile replaced the leaving group, and everything else on the other side stayed the same. And notice we're drawing out all this other junk here, and that's because it's going to play a role in what's to come. So normally we just wrote a boring old R group, but now we're expanding to what's attached to the carbonyl carbon. All right, so we're going to do a mini mechanism. That's kind of like a cheater mechanism, just to kind of get us through to jog our memory. Nucleophile attacks, open close, kick. AOCK. So that's not the thorough one, but if you're just trying to kind of, sort of get through a concept, it's okay. All right, so attack, open, close, kick. Now, in contrast to that, we expect the next one to be attack, open, protonate. That means the leaving group never left. It stayed. So that means it never was a leaving group. So, the specs say that Z is not a leaving group, i.e. Z equals H or R, ketone aldehyde. Oops, I should actually say that in the right order, because if it's H, it's an aldehyde. If it's R, it's a ketone, respectively. And what was the name of that reaction? It can't be substitution, because we didn't replace the leaving group, because it wasn't a leaving group. The group stayed there. So we added the pi bonds gone, so it's an addition reaction. All right, nucleophile once again, as you expect, behaves as a nucleophile. So instead of doing attack, open, close, kick, we do attack, open, and I'm gonna do a fancy open protonate in one step. Watch this. Open, grab a proton all at once. And that's actually not a cheater way, that's an advanced way. It really is legit. Watch this. If you notice, the electrons are coming off of this carbon, right? They are belonging to the oxygen now. And as the oxygen, you kind of think of them kind of pivoting off, and the oxygen's right here. And then it grabs a proton, and now they're stuck on the proton. So it's a very condensed way of doing it. And I think you're ready for that when we're doing, kind of rapid sort of reviews. So attack, open, protonate. So I'll review that here, AOP. Nothing wrong with writing out every step if you still feel inclined to do so. All right, attack, open, protonate means Z stayed there. In fact, let's just fill it in with R or H, shall we? Because we know that's what that really is. Tetrahedral intermediate now has a stereocenter. We know that for sure. New group is the nucleophile. O opened up to OH after protonation. And then we have all of this stuff that remained unchanged. Okay, now what are we writing all that other stuff for? clearly that H must be important because that's the only spot the difference, right? So yes, if you figured that out, good for you, because that is what is going to be significant here. Why is an H adjacent to a carbonyl carbon significant? We have actually acknowledged that before. Way back in our simple acid-base chapter, we have noticed that if we said, hey, by the way, what's the most acidic proton in this molecule that happens to have a carbonyl? You would have picked the one adjacent to the carbonyl because cario resonance. Take this H off, you have a lone pair next to pi bond, resonance where you can delocalize the negative charge into an oxygen. So hence, very acidic proton there. So we could say carbons that are attached to a carbonyl carbon have very acidic H's. That's a mouthful. So luckily we could have some more terminology at our fingertips or disposal. We can actually call this an alpha carbon. The alpha carbon is a carbon that's attached to the carbonyl carbon. The alpha carbon has an H that's very acidic, or we can even say alpha protons. So they are easily removed by a base. So the specs for this reaction, we're going to say Z is not a good leaving group. Okay, so Z is going to be R or H usually. And nucleophile, as we know, they can actually also act as a base. And in fact, we will probably tailor it so that it's a better base than a nucleophile, because remember, you can do that. So let's call this a base. What does that mean? It's not going to attack a carbon. It's going to pick up a proton. You can think of it as attacking the proton if you prefer. Okay, so take the proton, leave behind those electrons. This is a simple, this is our next reaction, but it's a simple acid-base reaction. It's not simple in the end because it's what we do with this now. We say, wow, bazinga, we have this carbanion. We have a carbon nucleophile. Just say that again, carbon nucleophile. That's a whole world of possibilities right there. That carbon can make a bond to other things, like carbons. So, big deal, which is why this just opened, I wouldn't say a can of worms, because that implies a bad thing. It opened a good thing. Whatever a good can of worms would be. This is very good. Very exciting. So, carbon nucleophile opens like unlocking a secret door. In some of my favorite video games, you would do that. You'd unlock the secret door and get very excited. So that would be a better analogy. So you just cue the unlocked secret door, the rest of the map is revealed, and you connected two maps. That's very good. So carbon nucleophile. So I'm going to write that down. That's not the official name of it, but synthetically speaking, it's important to keep that in mind. Okay. All right, so let's put R or H. Now what? I also want to demonstrate why, just to remind ourselves, why that proton was so acidic. It's all about stabilizing that conjugate base. Look, remember how this has resonance? So let's show that conjugate base resonance through that oxygen. Okay. So this has a name because this is a carbon nucleophile, and that is a significant thing. Remember, I've told you that unlocks the door. Thank you. That is a significant thing. That means that we can make new bonds, and so it has a name. It's called an enolate. Why enolate? So I'll put that down here too. Might sound like a familiar term. Oh, I forgot to write the whole name of this reaction for you, which is enolate formation. Okay, so why Is it called the enolate? That might be reminiscent of a term you've heard before, I hope. Well, I know you've heard, but I hope it rings a bell. So let's draw out this guy and see if we could see its familiarity. It's an alkene with that's also an alcohol, i.e. enol. So an enolate is got the suffix ate, indicating that there's an oxyanion, so O-. So in other words, the alcohol's been deprotonated. So the enolate of this enol would be this guy. So can you see how that's an enolate now? And that, oops, I took it off the screen, sorry. Can you see that that's an enolate, and that would be an enol if it had the H right there, right? So enolate. Now this is also an enolate. It does not have a alkene shown, and it does not have an alcohol deprotonated shown, but it's the resonance structure of this. And remember, resonance structures are equivalent compounds. So I can draw the enolate this way, I can draw it this way. And in mechanisms, I will be interchanging them. So will your book, so will other sources. So you want to be able to do that too. In fact, sometimes it's easier to just go, it's shorter to just use this one, because that's the first thing you form. It's more arrows to use this one. Although if you say which is the most significant resonance contributor, you could argue this one because the negative charge is on oxygen, right? So that's a better host for a negative charge. So this would be the more realistic contributor to the resonance hybrid. So I think either one has a valid argument for appearing in a mechanism. So either would be correct. So be comfortable using both. I'll try my best to kind of interchange between them frequently so that we get used to both. Okay, so let's get comfortable with this again, because we got to get used to going, for the moment, out of nucleophile mode into base mode. And then we're going to go back into nucleophile mode. So we're not, plus base mode. So we're kind of building up to that. And it's actually fun and exciting. So we're gearing up for the best part. In fact, the next chapter is one of my favorites. And so I'm excited to be leading into it. And so if you can't tell, I know it doesn't always come off that way, but it's good stuff. All right, so base, acid-base reaction. We're going to take off that H again. And there's a reason I'm doing this again, but oops, I don't want to draw the... All right, so what are we doing there? Showing an equilibrium, right? So I could also say, well, why not show the other method, the enolate? So I apologize if you've already written this in pen. You're going to hate me, but I can do this. How about we draw? How would I show in one step showing the enolate? It goes there instead of lands on the carbon and goes there. So you're going to see both ways of deprotonating. Okay, so you can go there right away to what looks like the enolate more realistically, right? Which is the more significant resonance contributor. So the previous mechanism I did in the box, you know, why don't I, just for clarity, so everyone doesn't hate me, superimpose them with different colors. So I could have also done this right there and let the proton land there, and then that would be this equilibrium. Get my myself some room for the blue. Now that would be the alpha carbon. That's an anion now. That's exactly what we did before. So you are going to see that first step represented either the red way or the blue way, and both are correct. Okay, so the red way is this one. And then furthermore, these are interchangeable, right? So if I were to, how would I show that? if I were to draw this way, and how do I show that this is interchangeable? Then I just draw the resonance structure, right? And if I wanted to go from this one to this one, I drew resonance going down and back here. So there's just more arrows to be comfortable with. All right, so we have I want to also point out this is a relative of enol. So this is a good time. We've talked about tautomerizing before. If we call this the keto form, you should be able to quickly recognize if I say tautomerize that to the enol, you should be able to say, well, that would look like this. Z, carbonyl turns into OH, alkene with the R and the R, right? And what you do with an enol is effectively this H became that H, right? So I'll write that out, tautomerize. So we're going to be using a lot more tautomerization steps and just taking advantage of that. You might want to do this mechanism of the proton transfer as well. And then thinking about this equilibrium, it's not easy to take off that H even though this is relatively acidic. Because look at what we're asking it to do. We're asking to make a negatively charged species, number one. And number two, even though we see that the better structure has a negative on the oxygen, we still end up losing the CC double bond, and we know that in the keto form, that's actually favored. So if we just revisit what's going on here, let's see. Sorry, my tech is acting up. Okay, enolate formation. Okay, so left side of equilibrium, I mean, we had a non-zero formal charge once we did it, so zero formal charge. And CO is stronger than CC. Okay, so this was the exciting part. The fact that we can form this enolate unlocks the world of possibilities of carbons attacking other carbons, make a carbon nucleophile. So an enolate is a nucleophile. That's a big deal. Okay, so you're going to be, we're kind of slowing down and just making sure we're revisiting this acid-base stuff just because we're making sure we know how to form the enolate properly, because then we're going to start using it like crazy. That's when we get to the aldol part. So the enolate itself, we need to be able to say which H is coming off. And sometimes there's more than one alpha H. So let's call this, for example, this one with two carbonyls, a dicarbonyl compound. Let's call this the red alpha. You could do alpha 1, alpha 2, but if you have multiple colors, even better. The blue alpha or the green alpha. So there's three alpha carbons. And each of those alpha carbons has two alpha H's, one of which would come off with a base. And let's just say we had one equivalent of base that would take off one H. Which H would it take off? A red one, a green one, or a blue one? It's going to take off the one that has the most stabilized conjugate base. So if it takes off the red one, we have an anion here, which is resonance stabilized with that carbonyl. So all alpha H's will be resonance stabilized, all of them. So it's a matter of which one has the best resonance stabilization or the most resonance stabilization. So this one and this one are alike in that they both are resonance stabilized with one neighboring carbonyl. This one is better or more desirable or more stabilized because it can delocalize between two adjacent carbonyls. So this is the winner. Here goes. most resonance. Right? So it goes between the two carbonyls. Okay, we are going to start doing some reactions that are beyond acid-base reactions. We're going to start with one of the oldest, most famous reactions called the haloform reaction. So what does that entail? Let me just show you a generic overview of the haloform reaction. Take a look at what changed. We have an X, halogen. XX is like a chlorine or bromine or iodine, right? So we've installed, I'll write that down, installed Br, Cl, or I on an alpha carbon. Okay, so that's useful because you effectively made an sp3 alkyl halide, which we know we could do lots of things with that. So that's a good reaction to have. And now, what does the bottom mean? It means we could do that under acidic conditions or basic conditions, and of course we'll visit both. And that's kind of a theme throughout the classes, that we'll want to know how to do something under either condition, because one of them is usually preferred. Now, in the old days, spectroscopy was not available to tell chemists what was in their unknowns. So if they're trying to identify the structure of a compound, or at least the functional groups present, they couldn't just put it in an IR. So one really popular test was this haloform reaction, or also known as the iodoform test, specifically where they used I2. And it was a way to detect specifically methyl ketones, because if your R groups are methyl and you have basic conditions and you have 3 alpha H's, you can excessively halogenate, and then if you add 3 halogens to a carbon, you now have a CX3, which is a good leaving group. So you could displace it with OH minus. So then we attack the carbon like we did in the old days, the nucleophile. By old days, I mean like a week ago. So you did attack, open, close, kick. And now we have a carboxylic acid. So you can go from a ketone to a carboxylic acid, and you see this CI3H. That's the haloform. So chloroform is the most famous haloform, CCl3H. But iodoform is Ci3H, so that's why it's called the haloform reaction, because you could also do it with bromoform. So it forms this as a byproduct, but it's really obvious. That arrow down means you form this nice, obvious solid, and it's white. So that dropping down is a precipitate. And so it's a qualitative test as opposed to quantitative. It's a qualitative test to tell you a methyl ketone's present. And qualitative tests have their place. I say, prehistoric times, like pre-spectroscopic. You can't take spectroscopic instruments everywhere. We can't walk around with NMRs and IRs and GCMSs, at least not that easily. So it's useful to have a qualitative test. A lot of drug tests are, urine tests, like pregnancy tests, etc., are qualitative. They're simple color change type tests, or they look like they're there or not, and they're prone to false positives, but at least they give you the direction of whether something could possibly be there or not. So this is useful, and they're still useful for that purpose. In fact, I've done this reaction. I think it's fun. In fact, I'm going to let you see a real demo by inserting a clip right here. Folks at University of Illinois, Urbana-Champaign, chemistry department, of course, put out this really nice video demonstration of the iodoform reaction. So that means it's the haloform reaction, in which iodine is the halogen of choice. So remember, in the iodoform reaction, you need to prove that a methyl ketone is present. So a methyl ketone that was used here is acetone. So in the first test tube, which is colorless, has acetone mixed with base. So this is done under basic conditions, which is necessary for it to go all the way to the haloform or iodoform in this case. So the base in this case is NaOH, and to that basic solution of acetone, this characteristic brown color of iodine / I- is added, and you can see you would expect sort of that color to diffuse, but instead the reaction happens so quickly that it turns milky as the solid crashes out of solution. So let's take a look at that in action. There it goes. Wow. So very fast color change. You don't see that uniform color of the brown. As the brown is even added to the colorless, it immediately gets milky, which is indicative of the dispersed particulates. If you were to sonicate it or centrifuge it, you would see it settle as a pile of particles at the bottom and a nice separation of the solid and liquid. So something very rewarding about that. Let's watch it again. There we go. Very nice. Haloform reaction. That's what you could see why it's such a useful qualitative test. It's very obvious that there is a methyl ketone present. And when we look at that movie, you'll see this really nice solid just kind of come out of solution, and it's kind of rewarding actually to see that that iodoform. At first you see that I2, which is very brown in character, you know, like that's very classic iodine color, and then you see this white solid just kind of cloud up the whole solution, and that only can happen because the ketone is there to convert it to that white solid. All right, so how does that work? Let's take a look. Mechanism. We're going to work our way there. This is not a methyl ketone. I'm not going to do a methyl ketone yet. I'll do one step at a time. I'm going to do only one H instead of 3 H's. Okay, so we have a H that's going to be pulled off by a base. There's our base, sodium hydroxide. And because we have only one H, we cannot, it's not a methyl ketone, we cannot get the iodoform, or bromoform in this case, to be what forms. So the product, before I go on, I'll draw that out, is simply going to be replace the H with a bromine. Once again, useful. That matches the template in the blue box in the previous page that I scrolled up from. So let's show how that happens. Grab the H, leave behind. Now I'm going to do the enolate this way this time. And I'm also going to draw my phenyl ring as a pH to save some time and space. All right, so now bromine is right here. We need to get that in there. And we're going to attack the bromine. Close. That will compel these electrons, the pi bond, to open and attack here and kick off that bromine. And there we are here. So let's track those arrows again. Carbonyl reformed, carbonyl reformed. Pi bond's gone, pi bond's gone. Electrons from pi bond stayed on this carbon and shared with bromine. There's that new bond right there. Okay. All right. So while we certainly prefer to go in the lab these days to unequivocally figure out our structure by NMR, synthetically this is still very useful, because here I didn't do this just to get, I wouldn't get that white solid crashing out because I don't have a methyl ketone. This is still used just to replace one at a time. We only had one H to replace, so we only got one halogen on there. So we got a halogen at the alpha carbon. I wrote that above. I'm going to write that again because that's just an important point. Replaced alpha H with Br. Okay. Now, remember it said it could be done with acid or base. So how does that happen with an acid? And the acid is often, specifically this acid. What is this acid? Acetic acid. It can also just be written as aqueous acid, or H3O+. Okay, so let's allow it to grab some, pick whichever acid is provided, and in either case you need it to grab an H. Why am I letting that grab an H? Look at that whole compound. We have the lone pairs on oxygen, and we always activate our carbonyl if we have an acid. Same thing here, we're gonna activate a carbonyl. I'm gonna draw the pH out because it's not part of this party. And by the way, let's draw the product. We know what it looks like. So that helps us kind of get our mechanism to match it. So that's our goal, but we're trying to show how we got there with the acidic conditions. So here we go, activated carbonyl. Why did I activate a carbonyl for nucleophilic attack when I'm spending all my time attacking the alpha carbon by taking off its proton? We kind of do attack the carbonyl in this way, watch. Conjugate base of your acid, either the water, since I chose to use H3O+, I'll use the water, but if you're using acetic acid, use the carboxylate. It will come and take that H, and that H will leave behind the electrons here to kick open that pi bond. And we form an enol. OH. Now we have an alkene here, right? Yep. Okay, so we have an enol. You might say, oh, I'm going to tautomerize it. You can say that, but if you do, you end up there, which means no reaction. So we could have also shortcutted this and say, so you might see this in some texts. Instead of seeing the entire mechanism, you might see the double-ended arrow that simply says tautomerize. And once you feel like you know that mechanism, you can do that too. Usually I do that after an exam. I see sufficient understanding of tautomerization, I allow that to be shortcut. So to go from the keto form, we know we need the enol. Why do I need the enol? Because I'm going to use that pi bond like an enolate, only I don't have a negative charge because I'm in acidic conditions. It's going to be just like an enolate. So notice it's an enol, it's an enolate that's protonated, hence enol, right? So what does an enolate do? It attacks, it's a carbon nucleophile. It attacks electrophiles. And what's our electrophile? The bromine. So I'm going to use this like an enolate that's just been protonated and let it attack that bromine. So how can I get that to attack? Remember, use these electrons to push it down, to drive that. So close and open up that pi bond, kick off the bromine. So then we end up with the phenyl, carbonyl that's protonated. We are almost home. It's a simple deprotonation step to get there. And remember that bromide is hanging around, we just kicked it off as a leaving group, so it could pick up the H for us, and we get here. Okay, so same product, whether you use acidic conditions or basic conditions in this case. Okay, many times when we do this reaction, the solvent is actually the one that was shown there, acetic acid. So you might have the word drawn out, you know, acetic acid is the major component of vinegar, because it's a good solvent, and then it could also serve the purpose of your acid. So when you're trying to learn this mechanism, kind of think of it as two parts. you're going to tautomerize. And this is a good time if you've been seeing me tautomerize by just writing the word tautomerization. And you're saying, but I don't remember that mechanism. There it is, right here. So this is a good time to review that several times because it's still coming up again in the future. So there's two parts to this mechanism. The tautomerization, which I most of the time take for granted is understood, but if it's not, nail it down now. And then the other part. So let's describe that. So part one, acid catalyzed tautomerization to form the enol. Part two, you get your enol, you let it be the nucleophile to form the halogenated product. Okay, so two major parts. Okay, so let's do this again, but we're not gonna, I think it'd be good for you to go ahead and draw the mechanism for practice. I want you to just predict the product with me. Acetic acid, acidic conditions. Bromine. Here's our alpha carbon. Draw your H's. Ooh, we have more than one H this time. Okay, it turns out, what are we gonna do? Are we gonna add one H, one Br or two Brs? It turns out in acidic conditions, only one is added. And that's because it's just not quite as reactive, right? It's not as hot when we have the nucleophile as a neutral, right? So compare those two mechanisms. That's why we drew both of them. You would see that one mechanism, you could see is clearly not quite as hot as the other mechanism. So this is different than what happens in basic conditions. So I'm going to write that down. Only one Br added in acidic conditions. Two alpha, even though there's two alpha H's. So that's written again in this sentence down here. When an alpha carbon halogenation occurs with an acid catalyst, the reaction generally substitutes just one hydrogen atom with a halogen atom. Take that same reaction, use a base instead, we will have a different result. Okay? So both will be substituted. So I'm going to write that down. Replace. So these were the two H's. After you find your alpha carbon, you say, okay, those are my two H's. You replace both alpha H's with two Brs. Okay, so I'm going to let you draw the mechanism for practice because we've already done the mechanism under basic conditions. But just the thing to remember is that why does one keep reacting and one not? Just look at the difference of our nucleophile. This is our nucleophile under acidic conditions. It's attacks. And under basic conditions, it's this guy. Who is more reactive? O minus that drives down those electrons, or OH. Clearly O minus is more reactive than OH, right? It drives the electrons down. So that's just enough of a difference that this is too slow to keep reacting, whereas if it's basic conditions, it will. So that will give us a different product. One bromine, two bromines. So we're going to summarize that there. When alpha carbon halogenation occurs with a base catalyst, the reaction generally substitutes all hydrogen atoms with available halogen atoms. So the special case, which is the lovely iodoform reaction I started with, only occurs when one of the alpha carbons, so this is alpha carbon, but there's no alpha H's, right? Has 3. It's a methyl ketone, has 3 H's on it. So this is a methyl. You have to have a methyl attached ketone. 3 alpha H's. When that happens, we replace all H's with bromines. So we do that mechanism, previous mechanism, 3 times. So bromine, bromine, bromine. Okay, it does not stop there. We do not isolate the 3 bromines on the carbon. Why? CBr3 is a great leaving group. We just made a great leaving group, and we have base present. Bases can also be nucleophiles. So it acts as a nucleophile, and it comes and it attacks, opens, your old friend, that mechanism. So I'm drawing pH for the phenyl ring, O minus. Who's there? Our new friend, the OH, that nucleophile. And I'm going to write CBr3. Because we have a good leaving group, close kick. Okay, OCK, once again. All right, so CBr3 comes off as our byproduct. That's, that's a minus right there. And it will add with an H plus eventually, get neutralized to be HCBr3, and that's bromoform. That's like I said, that's our byproduct. We're usually looking for what's going on in the organic sense. So we have, I'm going to draw out my phenyl completely now, or my benzene ring. Closed back to the carbonyl, kicked off the CBr3, we are left behind with the OH. Look at that. I have a carboxylic acid. That's actually a big deal too, because until now, if we have a ketone, we're pretty much stuck with a ketone. The only exception would be the Baeyer-Villiger, right? Good old Baeyer-Villiger, we can turn it into an ester, and then that opens up the carboxylic acid derivative chapter. This is the other door to the carboxylic acid derivative roadmap, right? So ketones and aldehydes are much less reactive, but if you can turn them into a carboxylic acid, I mean, think of the possibilities. Turn that into the acyl chloride, then a whole world is open there. So lots of synthetic possibilities. So you're never really stuck at a ketone if you have the methyl ketone. If you can get to the methyl ketone, then you can get to the carboxylic acid, right? So that's a big deal. That goes to the other, I might actually just make a note of that, because when we're trying to do retrosynthetic analysis, it's worth kind of keeping these big pictures. Connect to carboxylic acid roadmap. You want to do that. Thank you. Okay, summarizing this in words. If an alpha carbon undergoes halogenation with a methyl ketone and base catalyst, it forms a carboxylic acid and the haloform, which is why it is called the haloform reaction. So that's the exception. We don't ever get the 3 halogens on the carbon. It keeps going. We get the carboxylic acid. We can get 2 and 2. We can get 4 halogens on alpha carbons. We're just not going to get 3, or even worse, 6. Okay, so summarizing it, let's make a little list. In acid, what would that look like? We're just drawing the products now in a generic template. Methyl ketone becomes what? Instead of CH3, CH2X. One hydrogen atom of the carbon, alpha carbon, substituted with the halogen, right? So we get that one there. Base halogenation. Look, we have two alphas. What's that gonna look like? R, both will be replaced. All hydrogen atoms on the alpha carbon substituted with halogen atoms. Special case, if that carbon is a methyl, so if you have 3 alpha H's, and we're in basic conditions, we don't see that carbon's gone. You lose the carbon, and so that's kind of a clue also synthetically that happened. Maybe the haloform product is given as a clue. Before the methyl ketone forms the carboxylic acid, and the haloform. Okay, we've talked about opening some synthetic doors and connecting different roadmaps. So this would be the perfect chance before we go on to the next new thing, is to connect a lot of old ones with a practice problem. Retrosynthesis. If you could put this all together now, you'll feel ready to hopefully go on. And this one's not easy. It's got a lot of steps integrating old with new. So if you need to pause and take out your roadmaps and kind of get them all together, maybe kind of brainstorm how you'd work this out, that'd be a good idea. I'm going to keep on going. So what we're going to do is we're going to try to make 3-ethyl cyclohex and 1-one, cyclohexanone, from ethyl bromide and cyclohexanol. All right, so we're going to show the retrosynthetic analysis and we'll show the forward synthesis. We'll show the whole shebang. I'm just going to try to look for some really dead giveaways right away. So these are my only sources of carbon. And clearly I could kind of see where the pieces come from. So I have 6-membered ring here. So that's where that came from, right? And so the 2 carbons here must have come from here. All right, not so bad so far. All right, so that means I made a bond at some point here. That's a point of disconnection, right? And so let's number that. At one point we did, at that 3 carbons away from where the oxygen's attached. In fact, I can even number it starting with the oxygen and say 1, 2, 3, 4, and that's a 1-4 relationship. That's sometimes called a 1-4 addition. That might give us a clue. Also, I noticed that the OH is not an OH anymore. It's a carbonyl. So we have to turn that OH into a carbonyl. And in fact, because we've been doing so many carbonyl reactions, there's a good chance that we're going to use carbonyl-related chemistry. So we might want to do that really soon, actually, because we know that alcohols have to be protected and they interfere with all kinds of reactions thanks to that proton. So when I do retrosynthetic analysis, yes, I go backward like this, but this is kind of like a showing your work spot. And I try to think of what did this used to be. And maybe this was usually some sort of halide. I mean, that's what I started with, but I'm not sure yet, right? So if I'm kind of stuck there, I start to go forward as well. So I know that I have this, and I need to get here. That's something we all know from an old reaction, PCC. That'll do that, or Jones. Okay. And so, but I know that so far I can attack the carbonyl carbon. I can also do things with this carbon. I'm just starting to get into that in this chapter. But have we learned how to do something? So this is what we would describe as the alpha carbon. We describe that as the beta carbon. Have we learned to do anything with the beta carbon? Only one thing. The Gilman. Let's bring back the Gilman. To have a Gilman, you have to have an alpha, beta, unsaturated carbonyl. Okay, so you have to have an alpha, beta, unsaturated carbonyl. So that means if I'm going to, so it means it had to look like that. And if this had to be a Gilman reagent, that means I couldn't have had this. I had to have Cu, so there's two of these, CuLi. But good thing, I can actually make that from the ethyl bromide, right? All right, now what? So in other words, this plus that gives me that, followed by a water workup. So that's the Gilman reaction. But this is not, I showed how to go to here. I did not show how to go to here. So how would I go from here to here? So that's kind of a missing middle piece. So I could say, okay, this used to be that, or how do I go that way? Well, I have an alkene, right? How do I get an alkene? Elimination. How do I do elimination? So I need to go back more steps, actually. So I'm going to undraw those arrows and say, well, I'm an alkene. I must have done elimination. How can I do elimination? I had to have a halogen, a leaving group. Let's pick halogen because we're working with halogens right now. Maybe we'll use that reaction. How about I put the halogen on the alpha carbon because I know how to get one there. Aha. If I go do that and then I go the forward way, that would be a base. That'd give me a good old E2 to give me an alkene there, right? And then I know how to get here. That's the reaction we just learned. I only want one H to be replaced, not both. So I'm going to do Br2 in the presence of acid, not base. So notice how this is retro and forward kind of at the same time. All right, so I'm going to put this all together. I think I have the rough idea. So first I'm going to take my ethyl bromide, and I'm going to convert it to my Gilman reagent. So step one, lithium, and so I can make the organolithium reagent, and step two, CuLi. And so now we're going to have Et2 CuLi, and this is to be used later. Now I'm going to take my organolithium, actually sorry, not yet. I'm going to take my cyclohexanol and oxidize it. Here's my ketone. Now I'm going to install the alpha halogen, Br2 with acetic acid. Where are we here? Now I'm going to do some old-fashioned organic 1 E2 elimination. Let's put our friend sodium ethoxide in there, NaOET. Just trying to do an E2 so I can get an alkene. All right. Now we have our alpha beta unsaturated carbonyl. Now Gilman, when we first learn about it in that organometallic section, seems so weird and esoteric and out of the blue that a lot of students just want to block it out because it's traumatic to see something that's weird. Unfortunately, alpha beta unsaturated carbonyls are not weird. They're very common, and they're going to make a big comeback. So the Gilman was just kind of there to warm you up for that. It's not going anywhere. It's going to be brought back with a vengeance, as well as all of its friends. So just kind of open your arms and accept it before you try to forget about it, okay? That's why I incorporated it into this synthesis as well. Okay, so Gilman means that we do that conjugate addition, that 1,4 addition. So instead of it attacking the carbonyl carbon, it attacks the other electrophile when we have the 1,4 alpha beta unsaturated carbonyl, this one, that carbon. So this is 1 ET2 CuLi followed by water workup. So remember it's like a Grignard, only the Grignard's more aggressive and attacks the carbonyl carbon. It takes its time and it attacks down there. That's a dead giveaway, it's Gilman. If you're 1, 2, 3, 4 away from the carbonyl oxygen, it's a 1,4 addition, that's a Gilman. And then that we had 0 functionality on our ring. A good way to add functionality is get a halogen on there, leaving group, so we could do that E2. That was that most recent reaction, haloform. Okay, that was fun. I'm going to pause here so that you can get some more practice in before we dive in to the next thing we're doing, which is alpha carbons as nucleophiles to add more carbons on them instead of halogens. That's a big deal, and even more fun, I would say. But this is a cool chapter. So I hope you enjoy it, but kind of get these basics down, and see you soon. Thank you.